This is the second video in the concurrent programming presentation. Hopefully you listened to the first part already. We talked about this example that does multi-threading computation of checking numbers for primeness. And I think we did not touch on the actual thread objects themselves. I'll just briefly cover those. So I have a class called primeness thread big integer. It extends the Java thread class, meaning it knows how to behave as a thread. It has a constructor that accepts the number that I'm checking for primeness. The thread number I've assigned to this object, just arbitrarily give it a number so I can keep track of it. And the range that I'm checking in this thread, meaning that whatever num is, I'm going to use start, and I'm going to proceed all the way up to end, and I'm going to see if any of those are a divisor for num. And if none of those are a divisor for num, then this thread will return true, that it thinks, as far as it can tell, that num is a prime. If all of the threads return true, then that means that nobody found a divisor and that it is indeed a prime number. Theoretically, then, we could enable or add interprocess communication to this logic and then spread this thing out across an entire classroom and have the entire room doing prime number checking on a really big number. If you're interested, you might be able to make a couple of bucks. I think this contest is ongoing, I'm not sure. But if you have the time and inclination to either use an existing set of code or write your own code, you may be able to find the next prime number and make yourself famous and earn a little bit of money in the process. Our next demo will involve thread-safe concepts. So we've talked about how it is possible to synchronize the critical section in a Java program such that no two threads can be in that section of logic at the same time, and therefore they cannot interfere with each other. And that is a way to make a program run in parallel, to make a program be threadable. Another tool you can use is to make sure that if two threads are hitting the same data at the same time, then that data knows how to protect itself. And that would be considered a thread-safe data structure. This should be a phraseology that you add to your lexicon for the rest of your career. Anytime you pick a data structure in any application that you're developing, you should ask yourself if it's thread safe. And even if you don't care at the time, even if you think that the code you're writing will never be multi-threaded, you should still give consideration to thread-safe data structures, just so that's something you're always wondering about and always thinking about the possibility of adding. And we have this thing called Google that I'm sure you've probably all used at one time or another. It is a really good way to research these kind of topics. I did some Googling and I found a good example for us to talk about. This person, 11 years ago, asked the question, how do I make my array list thread safe? This person then realized that a Java array list is not thread safe. In other words, you can't have two threads going through the same logic or similar logic and accessing that data structure and then expect deterministic results. And we say then that an array list is simply not thread safe. And this might come as a shock. I mean, we probably all learned to use array lists in CS1. And it might be the first relatively complex data structure that you learned. I know I teach arrays, and then the next day I probably start teaching array lists, and I compare and contrast the two. Well, if we're teaching parallel programming, hey, not necessarily a good choice. But this person asked the question on Stack Overflow. Let me just try to get there. How about this? There we go. As we use Stack Overflow more, we learn some visual cues. One visual cue is the number of upvotes a question has, and 100 is a lot. So that means a lot of people thought this was a well-asked and interesting and useful question. That's a good thing to know. And 159 people thought this was a good answer. So we have a pretty high level of confidence in this source. By no means is Stack Overflow an authoritative source, but 159 upvotes from the Stack Overflow community is a decent indication that this is a decent place to start thinking about a solution. And this person was very brief. They suggested using collections.synchronizedList. And it appears to be simple. All you do is call synchronizedList, invoke that method, and you pass it the instance of your array list, and it will send you back something that is thread safe. And that's pretty neat. I hope you're a critical thinker, and I hope something that pops into your head pretty quickly is, what is the performance hit for this? I mean, we're asking for something that is more capable than an array list. And with capability comes overhead. So before I just simply implemented this solution without thinking about it, I would probably want to write some benchmark code and do some more research and find out what happens if I simply replace my array list with the object returned by this method. Does it slow my code down dramatically? And if anybody wants to do that analysis and write some Java code and do some benchmarks, I would certainly be happy to award some extra credit for that, because I'd like to see what you come up with. Back to the slides again. Whoops, took me to the beginning. I don't think you'd like to go through this again. Here's another example that I wrote just to make the point. Okay, my mindset in life is, if I don't understand something, write a program about it. That's just the way my brain works. And I find myself writing these little programs to prove things to myself. Total tangent, but forgive me. Total tangent. There is a problem called the Monty Hall problem. A lot of you probably never heard of it, but there was a game show called Let's Make a Deal. At the end of the show, they had something, I think it was called the big deal of the day, and they would show you 3 doors. You would pick a door. Couldn't see what was behind any of the doors. You would pick a door, and then they would reveal one of the other doors. Not your door, but another one. And then if that, you would decide whether or not you wanted to change your choice. So you haven't seen any doors, you pick one. They reveal a door, and then you can decide to change your door to the remaining door. And mathematically, it's an advantage to always switch. Conceptually, it's very difficult to grasp, but it works out. And I said a minute ago that when I don't understand something, I write a program about it. And this is one of those opportunities where I encourage you to read about the Monty Hall problem and try to understand it. I actually had quite a discussion with one of my professors in grad school about this problem. I won't mention his name, but he's a great guy, and some of you probably had him as well. But he was right, and he claimed that It's always to your advantage to change doors when you're given the opportunity. And I didn't believe it. I couldn't quite grasp it, but I wrote a program and hey, it turned out to be correct. I did a little simulation. Hey, always change doors. Sorry for the tangent. Hopefully that was somewhat interesting. Here's my example of thread safety. So I took an array list and I just pounded on it. And then I computed how well I successfully pounded on it. I have that loaded in my Eclipse, multi-threaded, thread-safe data structures. Let me clean up what I've already done. I'm in the main. And the first thing I'll do is invoke the method called demo not thread safe. And that's at the bottom. This one is going to launch 4 threads. And all 4 of the threads are going to hit the same array list at the same time. There are 4 million elements in the array list. There's my array list. I initialize all 4 million to 0. I know my starting condition, that the entire array list is filled with zeros. Each of the threads is going to go through the entire array list from 0 to 3,999,999 and increment each element. That's all we're doing is incrementing each element in the array list. Theoretically then, if this works, each element in the array list should now be 4 when this program completes. We should have 4 million elements, each of which is just 4 because they were all incremented 4 times. The logic is pretty straightforward. I start all 4 of the threads and I join all 4 of the threads and I wait. That's it. Now to find out how I did, I read the entire array list and look for the expected value 4 million times. I look for the value 4. If I don't find 4, then I increment my error count because I know something went wrong. What I expect to happen then is, since the array list data structure is not thread safe, I will find some elements in that array list that are not 4. They simply did not get incremented correctly by one or more of the threads. There's my thread. There's my critical section. The critical section is get the element from the array list stored in a local variable called temp, increment it by 1, and put it back in the array list. Very, very small critical section. Don't let your brain tell you that that's no way going to get interrupted. Don't let your brain tell you that it's so small and so fast we don't have to worry about it, because it will get interrupted and it will get multi-threaded. The logic of more than one thread will be going through this code at the same time. Let's run it. And it didn't run that. It ran the last thing we did. Let's run this main. How about that? There it goes. Let's see what we got. We launched 4 threads. We waited for 4 threads to complete. And 3 of those 4 million elements were not the expected value. 3 out of 4 million. Let's run it again. 4 out of 4 million. Let's run it again. 18 out of 4 million. We can see then that this is a non-deterministic result because we run it 3 times and get 3 different answers. We changed nothing in the code. We didn't change the starting conditions, didn't change the data. We get different results. This shows us that an array list is not thread safe. We can't trust the array list with these two simple lines of code. The fix then, as you hopefully realize, is that this little highlighted section of code, lines 35 and 36, need to be synchronized. They need to be locked so that only one thread can enter them at a time. And I'll leave that as an exercise to you. You can look back at what we already did, or you can do some research and you can synchronize that code very easily and you can get the correct result, which should be 0 errors. What's our next demo? We talked about the thread safety. And just harkening back for a moment, there would be two ways to fix this. I mentioned adding the synchronized logic to the critical section. You could also change the data structure. And if you look back at that Stack Overflow page that we just saw, instead of adding synchronization to the code, you can just pick a data structure that's thread safe. So there's two ways to solve that problem. The next example is a deadlock. A deadlock is a little different than a race condition. A deadlock is two threads, two or more, that hold resources wanted by the other one. So I have thread A with resource 1, thread B with resource 2, thread A wants resource 2, thread B wants resource 1, and they're locked. They can't continue until the other releases its resource, and the other can't continue until the first releases its resource. Therefore, they are deadlocked, and the program just freezes up. This is harder to find than just finding a critical section. This is a real logic debugging challenge in a lot of cases. I've cobbled up a very simple example. Here's a thread. Doesn't do very much, but it wants access to two resources. Okay? Lock 1 and lock 2. Those could be anything. If you look at the hierarchy of Java classes, remember from your Java work that the object class is the base class for everything you ever do in Java. There's a class called object. And in that class, there's a toString and there's some other things, but there's also a lock. So everything that you make, every class that you make in Java, since it inherits from object, is going to have a lock. And we can pass those locks around and use them to synchronize our code. In this case, I am saying that my thread, which is called my deadlocking thread, is going to use two different locks on two different objects. And I've got nested synchronization blocks. The first synchronization block, two nested synchronization blocks. The first one asks for a lock on the lock 1 object, and then once it gets that, it asks for a lock on the lock 2 object. So it needs two locks in order to get to this little snippet of code. The second nested synchronizations need the outer synchronized keyword needs lock 2. So once it gets lock 2, then it wants to get lock 1. And if you stare at this, you can see that there's trouble coming down the tracks, because if there's two threads running through this, the first thread eventually we'll get lock 1 and wait on lock 2. At the same time, the second thread has attained lock 2 and is now waiting on lock 1. That gives us a deadlock. If this is single threaded, no problem. When it becomes multi-threaded, eventually thread 1 is going to be right here waiting for lock 2, and thread 2 is going to be right here waiting for lock 1. Easy deadlock. Kick that off. Since it's non-deterministic, I'll just show you the main while this is running. I throw it into a loop. And I wait. And boom, that didn't take very long at all. Actually, usually it took longer. So you can see the output is stopped. Okay. And I'm deadlocked. I expected a lot more output because when I ran this earlier, it took several minutes. Let's try it again. Maybe I'll get better, more dramatic results the second time. Here we go. Okay, this one is trucking along. There's my loop actually that I said I had. So the loop is in the thread, and it's just inside the loop. Each thread is continuously asking for lock 1, then lock 2, then asking for lock 2, then lock 1, and eventually they're going to deadlock on each other. The output is just to make us feel better. If the output stops, then we know there's a deadlock. Now right now we appear to be at about 20, 21 iterations for each thread. Certainly those numbers are going to change because thread 1 isn't running at the exact same rate as thread 2. So those numbers will be close, but they won't always be the same. I'm going to hit pause, and when this thing deadlocks, I will come back. I'm back. It looks like approximately 83 iterations were required in thread 1 and about 81 perhaps in thread 0. But eventually a deadlock was achieved. Since this is non-deterministic code, we don't know what is going to happen. Notice over here in the console window of Eclipse that the program is still running. Okay, the red button is lit. So yeah, the threads are stuck. One of them is probably on line 29, waiting to get lock 2. And the other one is stuck on line 35, waiting to get lock 1. Since each of them holds the other lock, neither one of them is going to give up, and they will simply be butting heads for the future until you turn off the machine or click the terminate button. That's a really easily understood, simple deadlock. But you can imagine in extensive applications where locks are scattered, it could be difficult to debug a problem like that. Let's do a little bit with C. Not near as extensive, but talk a little bit about threading in C. There's a library called pthreads or POSIX threads. And we can launch a couple of threads and try to do some critical section work here. If you read the manual pages, this technology is mostly portable, but you know how C is. Here's our first example. I don't think I provided this one in GitHub or on Canvas, but it's easy enough to copy paste if you need it. It's very simple. In my main, I create a thread using the pthread type. pthread underscore t. The underscore t means type, so it's a thread type. And I call pthread create, which kicks off the thread. And the entry point of the thread is the third argument here, which is my thread fun or my thread function. This is analogous then to the start and the run that we saw in Java. The Java start method, the Java run method, sorry, would be up here, my thread fun. And the way you get there is by calling pthread create. And we don't have a JVM in the middle between us and the operating system anymore. So pthread create is making a request of the OS to spawn this thread. And then the next thing I do, similar to what I did in Java, is join the thread. So I don't want my main to finish and my thread to go away. I want to wait. Inside the thread, I don't do very much. I just print a message and I sleep for 1 second. When I wake up, I print another message and I return. I have this in my Ubuntu instance. There's that same code. Notice that I've included the pthread header to get the prototypes for that library, and the UNISTD header for sleep. Sleep's not that great because it sleeps in units of 1 second. So you don't have the resolution, the granularity that you had with the Java sleep. So I can GCC this, GCC pthread.c, and then why not turn on the warnings? And if I don't provide a reference to the library, I'm going to get a build error, a linker error. So I'm going to go -l pthread, and then run it. Not that exciting, but it does illustrate how to do a basic thread. A lot of overlap with the theory that we saw in Java. The next example is going to demonstrate how to create a critical section using a mutual exclusion lock, a mutex. Again, that's part of POSIX, so hopefully it's mostly portable. I did provide this on GitHub, so you're welcome to go grab a copy of it. This actually implements the John and Mary race condition that we saw earlier. And I'm going to flip back to Ubuntu again. And I don't have an IDE going, so I'll just look at this from the command line. I think it's called johnandmary.c. There it is. Let's look at the main first. This is right off the slide as well. In the main, I'm going to run this demonstration iteratively, in this case 10 times, because sometimes it doesn't fail, since it is non-deterministic code at the outset before I start using the mutex. And if you run it once and it doesn't fail, you end up running it 5, 7, 10, 20 more times, so I just wrapped a loop around it. My balance is 0. John's going to deposit $100. Mary is going to deposit $500. John has his own thread. Mary has her own thread. And then I join them. Now, looking at this code, Notice that this line, the pthread create, launches the thread. And then I add $500 to the Mary deposit variable. And there's a very good chance that by the time I get to this next line of code, it's already finished the John thread. It might not even be multi-threading in some situations. It's just there's so little code here that by the time I execute this assignment statement, this thread may indeed have started, run, and died. So I might want to rewrite this a different way just to force it to be a little more multi-thready. If I do run it the way it is, though, let's look up here at what happens in the thread itself. A lot of this is commented out. But the first thing I do is try to get a lock. And if I get the lock, then I can enter my critical section. And the critical section ends right here where I give up the lock. So it's not as obvious as the Java syntax because there's no braces, there's no indentation. But there's the beginning of the critical section where I request the lock. My thread will block right there. It will sit and wait until that lock becomes available. The lock is a global variable that everybody knows about. So each of the threads is hitting the same global variable. They don't have their own copies of my mutex. That would defeat the purpose. Each instance of the thread is hitting the same variable called my mutex. So I'm just going to get out of this and run it. GCC minus wall minus L pthread. Uh-oh. Did I spell it wrong? All right, I got it compiled. There's the executable. So now I can run it. And remember, it's going to run 10 times. And it does take a little bit of time to run because I built some delays in there to force the non-deterministic characteristics to appear. But since I have the synchronization in there, since I'm using the mutex, it doesn't fail. It says 0 out of 10 tests succeeded. I mean failed, sorry. So let's go back in. And let's remove the locking. The only thing we have now is our critical section. In the critical section, I grab a copy of the balance, I store it in a local variable called temp, I add the deposit to it, and I write it back to the balance again. Very quick, but again, not atomic unless I use a strategy like a lock to make it atomic. I also put some sleep commands in there to promote the non-deterministic nature of this thread. If I didn't have those in there, again, it would run so quickly that it's highly unlikely that the threads would interleave with each other. So it sleeps for half a second here, and it sleeps for a full second here, but only for one of the threads. So I'm making a valiant effort to randomize this a little bit. Okay, keep in mind that I am no longer defining a critical section. I'm no longer using the lock. So escape : WQ, compile this, run it again. Again, it's going to take a moment because of those sleeps, but right away it's printing out the errors. It found in 5 of the 10 cases that we had an error. 5 of the 10 cases because there was no critical section, because the threads interleaved, the data got corrupted. Now, as we were talking a moment ago, I noticed that these two threads had a little bit of a gap between them. There was a little bit of a temporal gap. Whoops, I don't know what happened there. Because, well, I think I did something bad. No, I didn't. There's a little bit of a temporal issue because I've got that assignment statement between the two threads. Therefore, I'm suspecting that this thread just flat finishes. Without those delays, it just flat finishes before the other one. So I am going to take some steps here to make these threads a little closer together in the logic, and maybe that will cause them to break in an even more interesting way. I don't know. I have edited the code. Now I'm doing the best I can possibly hope for, launching one thread, immediately launching the other thread. I still have the little sleep delays built in to the threads, so I'm still building in some real world delays, but there's no longer any logic between the two threads. So we had 5 errors before out of 10 attempts to run. Well, let's see what we get now. Escape : WQ. You know, I used to teach Unix in industrial training settings to Unix users. We would teach them Vi, and the configuration of our workstations was such that every time you hit escape, it beeped. And so when they were learning Vi, they were hitting escape constantly to get out of command mode, and it was just a beep fest throughout the entire room. It kind of drove you crazy. But now, thankfully, not as much of that in Ubuntu. Let's compile it. Let's run it. Remember, we took out the mutexes. It didn't help. We still got 5 errors. Actually, I'll peel back the curtain a little bit. I've run this many, many times while I was preparing this presentation, and I always get 5 errors. I think the code is just so small and so fast that it runs in a deterministically non-deterministic fashion, for lack of a better term. But it is broken. All right, this is the next slide in the presentation. I demonstrated that already. I showed you that it fails if I run it without the mutex, and it works consistently if I run it with the mutex. And that brings us to the end of the slides. So thank you for your attention. Bye-bye.